Alrighty class, in this video I'll be doing the second example in section 13.2. It says use the first derivative test on the function below to determine the location of any local extrema. If necessary, round any decimal answers to 3 decimal places. And before we begin, of course, we have to find the domain of m of x. Now you may have remember that the square root of a negative number is not real. So, is x squared plus 4x plus 5 negative for any value of x? And the easiest way to answer that question is to graph this function on Decimus. So if you were to do that, you're going to get a parabola that's over here in quadrant 2 that doesn't cross the x-axis. So not only does x squared plus 4x plus 5 never become negative, it never equals 0 either. So x squared plus 4x plus 5 is positive for all values of x and never equals 0. And that's going to be important for later. Okay, so let's go find some critical numbers. Actually, the domain then is going to be all real numbers. Now, let's go find some critical numbers. So we have to take the derivative of this function, and we have to apply the chain rule. So the derivative of this function is going to be 2x plus 4 divided by 2 square root of x squared plus 4x plus 5. And we're going to set that derivative equal to 0. And change all of the x's to c's. And the only time that this derivative is equal to 0 is if the numerator is equal to 0. So I'm going to set the numerator equal to 0. And we get negative 2. Now, I know that this negative 2 is a critical number because if we were to substitute negative 2 into the derivative would equal 0. And negative 2 is in the domain of m of x. Now we have to ask ourselves, are there any values of x where g of x is undefined? And if we come back to this statement that I wrote in blue right over here, that's going to help us right now. So we want to know when x squared plus 4x plus 5 is equal to 0. Because if it was, g prime of x would be undefined. And in this case, the answer is never. So the derivative is defined for all values of x. Now that we have our critical number, I'm going to create the two intervals that we're going to use. And we're going to identify a couple test points here. How about negative 3 and 0? Then we're going to write the derivative up here. I'm going to be very careful. I'm going to factor the 2 out of that numerator. And that's going to be divided by and that x is going to be a c. C is going to be an x. Okay, so if we substitute negative 3 into this expression, the numerator is going to be negative, and the denominator is going to be positive. So the derivative is going to be negative, so the function itself is decreasing. If we substitute 0 into the derivative, this is going to be a positive value divided by a positive value, so the derivative is positive, so the function is increasing. Since the derivative changes from decreasing to increasing at x is equal to -2, there is a local minimum at x is equal to -2, and the value is 1. And we get this 1 by evaluating the original function at x is equal to -2.